This calc example is going to be looking for some concavity, an inflection point, and then we're going to be looking for a maximum minimum as we go through this. So part of this is to recognize that when we do our derivative, we have a product rule, and we also have an interval, right? So as we talk about our maxes and mins, because we got to do maxes and mins along the way as we're doing our concavity, that we for sure will have a maximum and a minimum because we have an interval. So this graph won't go up and down forever because we're going to be only looking at a certain section of it. So let's go through all the math on this one. So there's going to be two layers of steps or process to figure out some of the answers to this stuff. So first thing we're going to do when we do our derivative is let's take this and make it derivative friendly. So to do that, I'm going to rewrite the square root as x squared plus 36 to a 1/2 power. All right, so second part is we're going to do our derivative. And our derivative is a product rule. So the derivative of the first times the second, so derivative of x times the x squared plus 36 to the 1/2 power, plus the first times the derivative of the second. So this is a chain rule, so we'll bring the 1/2 down, x squared plus 36 to a negative 1/2 power, and then times the derivative of the inside, which is 2x. All right, so that's our derivative. To figure out maxes and mins, we're going to need to set it equal to 0. We'll also need to clean this up because we're going to have to do a second derivative from it. So let's see if we can make that as easy as possible. So not much we can do with this. This I can take half of 2. That will go away. So let me start pulling this stuff back into radical form. So this is x squared plus 36 square rooted. And then here we're going to have a square root, but it's going to go into the denominator. We have an x and x that's going to go into the numerator. So we're looking at x squared over the square root of x squared plus 36. All right, so there's our little bit cleaned up version of our derivative, but let's make a common denominator on this. So let's multiply top and bottom by x squared plus 36. Square root x squared plus 36. So the good news is those two radicals are going to undo each other. And so we're going to have x squared plus 36 over this square root of x squared plus 36 plus x squared over square root of x squared plus 36, which becomes 2x squared plus 36 divided by the square root of x squared plus 36. So there's our cleaned up version of our derivative. I needed to do that to make it so I can do my second derivative, but I also need to figure out some critical points along the way. So critical points are figuring out when we have slopes of 0 or some potential undefines. So slope of 0 is going to come from us taking the numerator and setting it equal to 0. So a 0 slope is going to be 2x squared plus 36 equal to 0. And then the denominator, we want to set it equal to 0 because that would be an undefined slope. So that's going to be the square root of x squared plus 36 equal to 0. And then this, though, is actually never going to equal 0 because no matter what you plug into this square, it's going to make it positive times a positive 2 plus a positive 36. That's never going to happen. And then square rooting something, we're never going to get it equal to 0 in here because, again, positive plus the 36 is never going to get us a 0, so we can square root it to 0. So for our first derivative, it's telling us that we have no critical numbers. So, so no critical numbers in our first derivative, which means in the interval, we don't have maxes and mins, which also then means our endpoints are going to be some maxes and mins. And I don't know what those are, so let's just plug in -7. Let's plug in 6, and I would throw those into calculators and let the calculators figure out the math. If I plug in a -7, I would get a -64.5. And if I plug 6 into it, I would get a 50.9. So there's our minimum. So we have a minimum at x equaling -7, and we have a maximum at x equals 6. All right. Now the concavity part, which is the second derivative, which is us doing the derivative of this. So first derivative stuff, second derivative stuff. So we have a quotient rule. We also may want to think of this as this is a 1/2 power. So when we do our derivative, we may want to think of it like this. Like so, when we're doing our quotient rule that we're about to do. Now I could bring this up and I could do a product rule on it as well. I'm just going to leave it as a quotient rule and just kind of fight through it. No matter what, it's not going to be simple. So I'm just going to leave it like that. So if I start to do the derivative of the top times the bottom, I'm looking at a 4x 4x times the denominator, x squared plus 36, 1/2 power. So the derivative of the top times the bottom minus the top, 2x squared plus 36 times the derivative of the bottom. Derivative of the bottom requires chain rule. So we'll bring our 1/2 power down, and then it's x squared plus 36 to the -1/2 power times the derivative of the inside, chain rule. All right. So there's the derivative of the top times the bottom minus the top times the derivative of the bottom divided by the bottom. Whether you want to think of it as a square root or a 1/2 power, you're going to get the same result because that piece is going to be squared. So whether you treat it as a square root or you treat it as 1/2 power, it's essentially going to go away. So let's see what we can get on the top. So our second derivative, a little bit cleaned up. We're looking at 4x square root of x squared plus 36 minus, I can take the half and that, cancel those together. I can distribute this x into here and here. So that would be a 2x cubed plus 36x. And then this piece, x squared plus 36 to a -1/2 power. We're going to move that, but we're going to mess with that in a second. So, and then that's all going to be divided by our cleaned up x squared plus 36. All right, so here's what we got. We're going to do a couple steps to this. We're going to break this up. We're going to try to figure out some common denominators. And so I'm going to kind of do two things at once here a little bit. We're going to break this up into two pieces. And on this second fraction, I'm going to bring this down. So I'm going to multitask quite a bit of stuff here on this step. So I got an x squared plus 36. It's going to be over this denominator. Right? And then minus. I'm going to leave a little bit of space or something I'm going to add to that. Then I have this piece of 2x cubed, 2x cubed plus 36x on the top. And then this piece is going to join that piece in the denominator. So x squared plus 36. This one's going to come down just on this fraction because it was only on that fraction. So it's going to come down. I'm going to go ahead and turn it back into a square root. All right, we're getting there. So now I need a common denominator. So let's multiply this x squared plus 36, square root of x squared plus 36. All right, so that gets us a common denominator between the two. That cleans this up. So if I distribute this in, we're looking at a 4x times the x squared plus 36. When I multiply those two together, then minus a 2x cubed plus 36x. And that is over this x squared plus 36 in a square root of x squared plus 36. And same thing on this one. X squared plus 36, square root, x squared plus 36. Whew. One last thing. Let's combine our like terms. Don't forget that you're subtracting a 2x cubed and subtracting a 36x. So this, when we distribute this together, we're going to get a 4x cubed plus this multiplied together is 144x minus a 2x cubed minus a 36x over common denominator. All right, almost. So if I put those last pieces together, I have a 2x cubed minus 108. When I take 44, sorry, that's a plus 108. So plus 108x. And then that's on top. This is on the bottom. X squared plus 36 square root x squared plus 36. All right, so there's our second derivative, finally. And then we're going to find our zero slope and our undefined slopes. So our zero slope, which is really concavity, it's the derivative of the derivative. So let's just call it zero slope. Let's just call it a zero. We're going to take our top, 2x cubed plus 108x, set it equal to 0. We'll factor out a 2x. We'll be left with x squared minus 54 equaling 0. Here we get x equals 0. Here we'll get x is going to equal plus or minus the square root of 54. And then on our undefineds, we're going to take the denominator and set it equal to 0, which is this piece. We'll set it equal to 0 because essentially they're already in these factored forms. And we'll set the square root of x squared plus 36 equal to 0. So there's our undefined slope idea. But that, again, is not going to equal 0. That's not going to equal 0. So we don't get any critical numbers from the denominator. And actually on this, plus or minus, this is greater than 7 or negative 7, which is outside of our domain that we're talking about. So I can kick those critical numbers out, and I can just focus on the 0. So if I just focus on 0, we're talking about concavity. And I'm looking at, let's see, here's our concavity equation. So if I plug in a value over here, such as -1, I would get A -1 plugged into this is going to make it a -2 with a -108. So it's a whole lot of negative. And then divided by a negative here, that's going to be positive, and that's going to be positive as well. So that's telling us that we have concave down. And then over here, we have plugging in a +1, so positive and a positive. It's going to make that a positive. And this is still going to be positive. And so we're looking at a positive here. So this would be concave down, and this would be concave up. So we have an inflection point at 0. That's our second derivative, 0. So our 0 here is an inflection point. So we have an inflection point at 0. And we have concave up from 0 to 6, because that cuts off our graph. We won't include that. We will include the endpoint. And then concave down is the other side. -7 to 0. All right. So that was a whole lot of work to try to figure out all of our concavities. Really, it just stemmed from the fact that we had a complex problem. So that was concavity inflection points, maxes and mins on a product rule.